Okay, welcome to lecture here. We're continuing on where we left off last time. So we just got into sort of the new chapter here, if you will, or chapters again. This chapter sort of comes from a couple of different spots in our textbook. But basically, we're going to talk about molarity as we started talking about last time. We'll also talk, I'm sorry, we started talking about stoichiometry last time. We'll also talk about concentration, molarity, and kind of finish up talking about titrations here in this chapter and calculations that go with that. Okay, so last time we got to the point where we were just kind of touching upon, again, basic stoichiometry and sort of the idea behind stoichiometry. And remember, really, as we talked about last time, stoichiometry really is nothing more than just sort of a conversion factor. Um, and they're really just conversion problems. And as we talked about the other day, essentially, instead of going to a table to sort of find your conversion factor and stuff like that, we use the balanced equation basically to come up with a conversion factor. And that's because really in stoichiometry problems, we're oftentimes interested in a number of things sort of based off of the balanced chemical equation. We're interested in things like, how much product we would produce as a result of a reaction. We're also sometimes interested in if we know how much product we produce, how much reactants we started with. We could also even stay, for example, on the same side of the arrow. If we know how much of one reactant that we're using in a reaction, we could use stoichiometry to figure out how much of the other reactant, for example, we would need to put in there. We also could say on the product side as well. So if we know, for example, how much of one of the products we produced, we could also figure out how much of the other product would also be produced, again, using stoichiometry. So there's a couple of really important things when we do stoichiometry problems or sort of basic stoichiometry problems is it definitely always starts with a balanced equation. So again, if we do not have a balanced equation to begin with, nothing's going to come out right in terms of your calculation. So just like normal, whenever you're dealing with equations, you should always make sure that it is balanced. Once it's balanced, as we did sort of the end there last time, we could actually come up with what is referred to as the stoichiometric equivalence. And that's a big word to basically say kind of like the equality we get our conversion factors from. And it comes from nothing more than just the balance coefficients in the equation. So in this particular example we were looking at last time, we have 2, 1, and 2 for our coefficients. And what that means is we basically could call those the number of moles there are of each of those things in that equation. So we could say for every 2 moles of H2 we put in there, we can throw in as well 1 mole of O2. For every 2 moles of H2 we put in there, we should produce 2 moles of H2O. Every 1 mole of O2, we can produce 2 moles of H2O. And because these are an equality, just like any other type of equality that you would get, say, from a conversion table or something like that, you really can write 2 conversion factors for each. And that's what we have sort of down here and somewhere else around here. We wrote them, I think. But if we look here, for example, our conversion factors between H2O and O2, we could basically write 2 of them. Would we need to use both of them in the calculation as we talked about last time? Probably not. You may just obviously need to use just one of them in the calculation. But we can come up with, as we did last time here, actually 6 different conversion factors coming from the balanced equation. And this will allow us to really find all kinds of things based off of this equation, as long as we just know really one piece of information. Maybe we know how much reactants we're starting with, maybe we know how much products we're starting with. We could use these relationships really to sort of figure out, how much would be produced. Along with this, because it is a multiple relationship, as we talked about last time, using the molar mass again as our conversion factor to go from grams to moles is definitely something that we use a lot with stoichiometry. So there really is sort of, 4 basic steps that we sort of follow when we do stoichiometry type problems. And, if you sort of follow those steps, you usually will get there to what you're looking for in terms of your answer. So, for example, just in this case, if we had, 15 grams of water was produced, and we want to basically figure out maybe how many grams of H2 we started with, we can use stoichiometry to help us do that. So, for example, the first step of any stoichiometry sort of problem, as we'll talk about, is really this step right here where we talk about the balanced equation. So, obviously, in this case, we've already balanced equation. You should always double check to make sure the equation is balanced when you have an equation given to you. I would say probably if you see coefficients, it's probably going to be balanced. But if you don't see any coefficients, you probably should take a moment there and sort of balance it. Really, the next thing that you do in a really basic stoichiometry problem is you take whatever they give you and you really convert it into moles. So in this particular example here, we're starting with 15 grams of water. So that's where we would use the molar mass from the periodic table, 2 times 1.008 for our hydrogen, plus 16 for our oxygen there, gives us 18.02 grams per mole as the molar mass for water. So that really would be the kind of the second step that we would do here. We would take our 15 grams of water, we would use the molar mass again and convert it from grams to moles of water. And if you wanted to, you could get an answer at this point. You don't necessarily have to. You could kind of continue on with the calculation if you want. But if we did get an answer, not rounding too much here, 0.8324 moles of water. Now, this is typically the dilemma that we have in a stoichiometry problem, which is that one piece of information they gave us is really nice, but it really just tells us, about this guy here in this particular example. But we're really interested in getting over to our H2. Now, clearly, you can't go to a table and find a table that tells you how many moles of H2 there is in H2O or anything like that. So, again, this is where the stoichiometry comes into play in terms of going from one thing in the equation, which you're really not interested in, to the other thing, which you are interested in. And from that relationship, I think we kind of did it last. Actually, we're going with this one now. Where are we at there? There it is. We're doing this guy here. So that would be our mole to mole relationship that we would get from the equation. Again, just the coefficients there, nothing really calculated. From that equality, again, we can choose two conversion factors. And which conversion factor should we choose? We should obviously choose the one that's going to cancel out the units. So we don't want to keep water anymore. So we do want to use the one over here on the left-hand side. That's going to put the water on the bottom and now allow us to get to the H2 on top. And again, moles of water will cancel out. In this case, I could do this. I think it still should be 0.8324 moles of H2. That's actually the big stoichiometry step there in a basic problem, that mole to mole relationship that comes from the equation. At this point, you could be done if we wanted moles of H2, but we don't want moles of H2. We do want grams of H2. So very common in a stoichiometry problem, on the back end of the calculation, we need to convert from moles to grams. So again, going from moles to grams is still going to be our molar mass. So that for H2 would be 2 times 1.008. And we're going to use that as our conversion factor backwards, 2016. So the last thing that we would do would be carry on our calculation here. And again, we're going to actually multiply here by the molar mass of H2. Again, not water here because we've already converted away from water. Moles will cancel, leaving us with, and we'll call it 1.7 grams of H2 in this particular case. And that's a lot of times step number 4 in these sort of basic stoichiometry problems. So 4 basic steps that if you just sort of follow from step to step in a basic stoichiometry problem will usually lead you to the correct answer. Any questions on any of those steps there? Now, what is a basic stoichiometry problem? Well, really, a basic stoichiometry problem is just that they give you really only one piece of information in the equation, and you ask for somebody else. So that's a basic sort of stoichiometry problem. These 4 steps. If something is done for you, you should just skip that step and go forward. Don't undo that step, which is very common. I've seen it done a lot for some weird reason. It's like, oh, wait, the second step I'm supposed to convert to moles, but it's already in moles. Let me unconvert it and then reconvert it. So don't do anything weird like that. If something is done for you, just kind of move forward. And that's basically what these sort of steps are talking about here, these sort of 4 steps. And everything really always starts with that balanced equation. So number 1 rule is make sure it's balanced. You want to convert whatever they give you into moles. That usually, again, is our molar mass that we need to use as a conversion factor for the periodic table. Using the coefficients, which is really the stoichiometry part of it, that mole to mole relationship. And again, you do have to sometimes convert out to different units. Remember that once you do this step here, you will always be in the units of moles if you did things correctly. If you didn't do things correctly, you won't be in moles, but hopefully you will. But you'll always be in moles. And again, sometimes you may want moles, sometimes you may want grams. Sometimes you may want some other unit like pounds, kilograms, some other type of unit. And again, it may require 1 conversion, 2 conversions, or something like that. That as well sometimes occurs up front. Sometimes you may be in some other unit up front that's not grams. So usually you might have to get it to grams first and then get it to moles. So that's also a very common sort of thing. Maybe you start with pounds or something like that. So there might be another conversion that you might have to do before you get it to grams and then take it from grams to moles. Any question on those sort of basic steps there? Okay, so why don't you give this a go here? Arrow's a little bit off there. We'll start the arrow there, maybe. All right, so CH3OH plus 3O2 goes to CO2 plus 4 water. If we start with 209 grams of methanol, that's methanol, by the way, it's used up in this combustion reaction. How much grams of water will be produced? So I'm going to give you some information that will be helpful for you. Once you take a couple minutes here and see what you come up with. Carbon is 12.01 grams per mole from the periodic table. We got some hydrogen there, 1.008. We also got oxygen, which is 16. And I think that's all we got. All right, take a couple minutes here, see what you come up with. We're looking for how many grams of water would be produced if we threw in there 209 grams of methanol. Take a look and kind of see how you're doing. So again, in these basic stoichiometry problems, you just want to kind of follow those 4 steps. Again, I really know it's a basic stoichiometry problem because I'm really only given one piece of information, and that's kind of a key to kind of know. It's just a basic sort of run-of-the-mill stoichiometry problem. So I have 209 grams of methanol. The first thing you want to do is make sure you have a balanced equation. I see some coefficients. I'm fairly confident, since there's coefficients on everybody there, that it's balanced. The next thing that you want to do is take whatever they gave you, which in this case is the 209 grams of methanol, and you want to convert it to moles. So obviously, in order to convert it to moles, we do need to figure out the molar mass of methanol, hence why we have our periodic table information over here. So methanol is 1 carbon at 12.01. It is 4 hydrogens at 1.008. And it is, looks like 1 oxygen at 16 grams per mole. So if we add all that up and not squish it in there, looks like maybe we get 3204, I think. 3204 grams per mole would be the molar mass from the periodic table. So that really is, again, kind of the first part of the calculation that we want to do. Since we have grams, we want the grams to cancel. So the grams will go on the bottom here. The moles will go up on top. Grams of methanol will cancel. Again, technically, you don't need to get an actual answer at this point, but I'm just going to kind of do it step by step. So again, you can see all the steps. This is 6.523. Again, I went around too much also, especially since we're going to kind of continue on. So what we did basically there is the first step there. Got an extra C in there, make that an H. So that is basically converting our grams to moles. Now, the problem that we have is we're really not interested in methanol here. So we want to then do step number 3, which is the stoichiometry part. So we want to go to the equation, find the one thing that was given to us, and the one thing we're looking to find, which obviously is water in this case. And remember, we could get the mole to mole relationship from that by simply just taking the coefficient. So that means that there's 2 moles of methanol. I don't want to put the extra C in there. For every 4 moles of water. And again, we're going to use that as our conversion factor. And that really is the third step and the big stoichiometry step here. Again, we have moles of methanol up on top. So to get rid of them, it's always opposite, right? To cancel things. So we're going to put the methanol on the bottom and the moles of water up on top. Moles of methanol will cancel, and that's sort of the third step there, which again is the stoichiometry part of it. So basically in this case, we're going to take our 6.52 times it by 4 divided by 2, and that gets us 13.046 moles of water in this case. At this point, we're close to what we want, but we are in the wrong unit since we are looking for grams. So what we're going to do is we're going to then need the molar mass now of water. So remember, sometimes people at this point will use the same molar mass, but you got to remember you obviously have converted now to water. So much like we saw in the previous example we kind of did together, water would again be 2 times 1.008 plus 16, going to give us 18.02 grams per mole as the molar mass for water. And that's what we would use here for our final step. Again, going opposites here. So moles on the bottom to cancel. Grams up on top to leave us with grams. And we will end up with about 235 grams of water. And again, this would be step number 4 in this sort of basic stoichiometry problem. Any questions on any of those steps there? So what does this number sort of really mean? Well, it means that if you did this reaction and you started out with 209 grams of methanol, everything went perfect. There was no side reactions. You didn't spill anything along the way, drop anything. You should get out and you should produce 235 grams of water. This is what is also sometimes referred to as the theoretical yield. Yield meaning produced, basically. So this is ideally the maximum amount, if you will, of water you would produce in this reaction if you started with 209 grams of methanol. Any questions on any of those kind of steps there? Okay. So let's try one more here. Why don't we use the same setup here, same equation and everything, except we'll change it up a little bit here. So let's say we started with 125 grams of oxygen, how many grams of methanol would we need? All right, so take a moment or two and see what you come up on that one. Again, same sort of numbers that we used last time would also be in play here. Okay, so let's see how we're doing. So again, basic stoichiometry problem. We really just got one thing given to us, which is the 125 grams of oxygen in this case, which is this guy. So same steps, obviously same equation as last time, so it's still balanced. Second step again is to convert what they gave us into moles, and we do need to do that. In this case, 2 times 16 for our old O2 gives us 32 grams per mole. And again, that's the molar mass of O2. We're going to use that as a conversion factor. Again, grams are going to go on the bottom so that they cancel. Going to leave us with moles of O2 up on top. And that will get us 125 divided by 32. Looks like maybe a 3.906 of O2. Any questions on that so far? Now we come really to the stoichiometry part. So they obviously gave us O2, and we're interested though in methanol. And again, as you can see in this example, we don't even have to cross over the arrow. We could do the same type of relationship here. And we see from the equation, for every 2 moles of methanol I throw in there, I for some reason don't want to write the formula for it correctly, gives me 3 moles of O2. Again, that's going to be really our third step here. We're going to use that as a conversion factor. So since we want to get rid of O2, we do want to put the O2 on the bottom so that they cancel, and leaving us the, I'll give it a try here one more time, methanol up on top. Moles of O2 are going to cancel. We're basically going to times it by 2 divided by 3. Going to give us a 2.604 moles of methanol. Again, still don't want to write the formula right for that guy. Methanol there. Any questions up to that point? So we're very close. We're at moles, but we do want to get the grams. Going to require us to get the molar mass of methanol. I'm just going to cheat and use what we did on the last slide since it's the same. So if you remember from the last one, it was 32.04 from the periodic table. So we're going to use that for our fourth step here to convert our moles into grams. In this case, we have moles, so we want moles on the bottom, grams up on top. Again, moles are going to cancel, going to leave us with grams, and that means that we end up with 2.04, 83.4 grams of methanol. Question on that step or basic stoichiometry problems. A couple of things. This is not a yield, right? So just because we calculated something, this is not a yield. A yield is only on the product side. So obviously that's not a product, so it wouldn't be considered any type of yield or anything like that. But basically what that number means is if you kind of want this reaction to occur and use up all of your 125 grams of oxygen, you need to dump in there 83.4 grams of methanol basically to do that. A good demonstration again, stoichiometry means you could do it as we did in this problem, stay on the same side of the arrow. You could do it like we did in the first problem where we go on opposite sides of the arrow. You could also, if you wanted to, again, stay on the right hand side of the arrow and stuff like that. Any questions on any of those basic stoichiometry steps? Okay, then let's talk about some non-basic stoichiometry type problems. And this occurs when we have what is referred to as limiting reagents. And limiting reagents means that they're called limiting reagents, they're called limiting reactants sometimes. And again, I kind of messed up all the arrows on this, so let me just redo this one here. So, in any type of reaction that we have, whenever we sort of react to things together, based on stoichiometry, there's always going to be sort of one reagent that sort of gets used up first. So, that reagent is what is known as the limiting reagent. So, the limiting reagent is basically the reagent that gets used up first. So, it's the reagent or reactant that basically will get used up first. There's something that's known as the excess reagent, which means you have plenty of it. You even have some leftover when it's all said and done in terms of the reaction because you have so much of it. So, why is sort of a limiting reagent important or non important? Well, it's important because if you need two things to make a product, for example. So, just a simple illustration of this. If you took A plus B to make AB, clearly in this case, you need to take an A and a B, put them together to obviously make our product. Now, let's say at some point during this reaction, A gets used up. What does that mean in terms of our product making ability here? It means we are in trouble in terms of our product making ability because in order to make our product, we need an A and we need a B. And now that A is used up, no more product will be made. And that's really why limiting reagents are important. Limiting reagents is really the reagent or the reactant that determines how much product you can actually make. So it's always the limiting reagent that determines how much product you'll produce. And again, it's basically the idea that as soon as that guy is gone, there's really no ability for you to make products, right? So I think they still sell it like this. Years ago, you used to be able to buy like a package of hot dogs at the market and you would get like 10 hot dogs. But when you go to buy the hot dog buns, you get eight. And in that case, obviously, you would have a limited supply of hot dog buns, be like your limiting reagent, and you would have an excess amount of hot dogs, like two hot dogs per package, right? And so it's the same idea in reactions. There's always something that gets used up first, there's something you have plenty of, and it's always that limiting reagent which determines it. In this example here, the O2 is in excess. Here at the end of the reaction, you can see we have some O2 molecules still around, which means that would be our excess reagent in this example. Our original NO there, I believe, was our limiting reagent. Our NO, which is the red and blue combination, there is no just red and blue combination left. And that means at the point where we lose our last one of those guys, no more of these products would be made. So limiting reagents, always the most important when you're doing it, a sort of problem, because it really is the one that will determine how much product you should produce. Any questions on that? How do you know it's a limiting reagent problem versus a basic stoichiometry problem like we've been talking about? It is really based on the problem. If you remember the problems that we just did, we pretty much were only given information about one thing, right? In limiting reagent problems, you are typically given information to calculate moles for all the reactants, which in most cases is like the two reactants in most problems. But you have enough information given to you in the actual problem, and it may be different units and stuff like that. But the ultimate thing that you want to look at is, do you have enough information for the reactants to figure out how many moles of those reactants I'm starting with? And if the answer is yes, it means that you do have a limiting reagent problem. So what does that mean in terms of working that type of problem? It means that you first need to, at some point along the way, figure out which one's your limiting reagent. Um, and there's actually many different ways you could do that. So I'm going to show you one way, which might be new to you. But if you have another way you learned before and you like doing it that way, you can absolutely continue to do it that way. They all should get you in the same spot. There's like, 2, 3, 4 different ways you can kind of do these problems. But we're going to talk about one way here that's a little bit different. And it can be beneficial in a couple aspects because it can allow you to answer a lot of questions that you're commonly asked in limiting reagent problems. So very common questions that you're asked about is, A, how much product would you produce? Maybe how much of the other product would you produce? You're also very commonly asked how much of the excess reagent is left over. So the way I'm going to show you, you can very quickly get to those answers without having to maybe back up and kind of start at the beginning and do a separate sort of calculation and stuff like that. So it's beneficial in that aspect. Um, it's also beneficial if you plan on taking 200B. It's kind of like the calculation you're going to do the entire semester in 200B, applied just a little bit differently. So it'll be kind of like a preview, I suppose, as well. So it'll kind of help you out maybe in that as well. All right, so let's take a look at one here together. And again, I'm going to kind of show you this method. And again, you can use it if you like it. Again, if you've learned another way, we'll talk a little bit about an alternative way as well, maybe a common way. You could do that method as well. So first off, let's take a look at this reaction. One process, we're taking 124 grams of aluminum. We're going to react it with 601 grams of our iron 3 oxide. What is the mass or grams of aluminum oxide that is produced? All right. Well, first off, I know this is a limiting reagent because if I look at the information given to me in the problem, I have 126 grams of aluminum. That means I can figure out how many moles of aluminum I have. I have 601 grams of iron 3 oxide, which means I can figure out how many moles of the other reactant I have. So as soon as you see you have enough information to get the moles of everybody, that should really scream to you that this is a limiting reagent type problem. And that's really the key to know that it is. So how do we go about this? Well, we're going to do what is sometimes referred to as an ice table approach. And in our circumstance here, the I stands for initial, the C stands for change, and the E here, we're going to call it end. When you take 200B, E will be equilibrium, which we're not going to talk about here. So, and right now we'll just call it kind of the end of it. And that's sort of an ice table approach. And it allows us, like I said, an opportunity to really sort of figure out, everything very, very quickly, or with very few sort of calculations at the very end. So the first couple of steps, though, even if we kind of take this approach, or really any approach that you do, is really the same steps that we did with a basic stoichiometry problem, which was make sure it's balanced. So we do have our equation that's balanced. Again, we got some coefficients, everything looks balanced. The second thing that you want to do is take whatever they gave you, in this case, both things, and we still want to convert them into moles. So really the second step is not that all different from a basic stoichiometry problem. We're going to convert each of those things into moles. And that means we're going to take 124 grams of aluminum. We're going to go to the periodic table, look up aluminum, and that's going to be 2698, I believe. Grams are going to go on the bottom, moles right there up on top. So everything cancels out. So if we do that, 124 divided by 2698 gets me 4 point, we'll call it 596 moles of aluminum. .596, right? Yep. 4.596. We're also going to convert this guy into moles. So 601 grams of iron 3 oxide going to the periodic table to convert into molar mass. Going to give me 2 times my iron, which is 5585, plus 3 times my 16 for my oxygen. Going to give me a molar mass for iron 3 oxide of 159.7, I believe. If I did not mess up there, let me just double check. 2 times 55.85 and plus 3 times 16, 159.7. Perfect. 159.7 grams per mole for iron 3 oxide, going to give me 601 divided by 159.7. That's going to give me 3.763 moles of iron 3 oxide. Any questions so far? Now, really, this ice table approach does need to be a mole. So that, again, that's why we're sort of converting these things into moles. So how do we go about setting up this ice table? Well, you set it up basically by, first off, rewriting the equation. So we're going to take our 2 aluminum plus our iron 3 oxide, our aluminum oxide, and our 2 iron. And now we're ready to do our table. So initially, this is going to be the initial amount of aluminum. So we'll have our 4.596 moles. This will be my initial amount of my iron 3 oxide, 3.763. So let's talk about products. What is happening here initially is we need these guys to come together to make products. So initially speaking, we're assuming that we do not have any products to start with. So we could assume initially that these guys are going to be 0. Now we're to the change part. And when we do ice tables, we typically use a letter to represent change. And that letter that we use is X. You can use any letter you want, really, but X is the most common one that is used. Let's also talk about what's happening with this reaction as we just did. Basically, this reaction is heading towards the product side. And because it's heading towards the product side, the I stands for initial. Yeah. So the I stands for initial in the table. So it's basically the initial moles here of your reactants and your products. But in our case, your products will always be 0. So it's really the initial moles of your reactants, which again is why we need to do this step first to convert them into moles. Other questions on that? Okay, so because we're assuming this reaction is going to the product side, what we know about the reactants is it should be decreasing the reactants, right? We have to use some reactants to make products. We also should assume that the product side is increasing. So what do we do to represent that? Well, our reactants become negatives or minuses. Our products is gaining, so they become positives. And we use negative and positive along with our x's here to represent that. So when we get to the change part, which is represented by S here, this would be minus, and it would actually be 2x. Now you may be wondering, where did the 2 come from? The 2 actually came from the balanced equation here. So this 2 is where this 2 comes from. Now you may say, is that important? And the answer is, it actually is. What we are doing right there by putting the 2 in there is we're actually doing the stoichiometry part of it. We're doing the mole to mole relationship. So if you do not put that coefficient in there, you will have the wrong mole to mole relationship and your answer will not be correct. So really important when you do the change part that you include the coefficient, because really what that is doing is the stoichiometry part of the calculation for you without necessarily maybe going and doing like a mole to mole relationship. Any questions on that? Now, the iron 3 oxide coefficient, although we don't usually put it there, is a 1. So this would just be minus x because it's basically 1x. Coming to our product side, again, we don't usually put the coefficient of 1 in, but I'll put it here so you can see it. The coefficient for aluminum oxide is 1, which means we would do plus because it's a product and x because it's basically 1x. When we get to our iron, the coefficient here is 2, which means this should be plus 2x. Any questions on the change part? Again, minus is on the reactant side because we're assuming it's decreasing with time. Plus is on the product side because it's increasing with time. And most important is the coefficients do need to be incorporated in that step. Otherwise, again, you might as well not do any of these calculations because you will be off for sure. Any questions on that? Okay, so what we're going to do now is go to the end here. And again, when you take 200B, it will be called equilibrium. But we'll go to the end. And what we're going to do is basically just carry down everything. I'm going to get rid of the moles just to kind of not make it so messy and stuff. But remember, these are moles we're dealing with. So this is going to be 4.596 minus 2x. This is going to be 3.763 minus x. And this is going to be x. And this is going to be 2x. Any questions on what we just did there? All right. So now what we're ready to do is actually determine what is our limiting reagent, what is our excess reagent. So to do that, we're going to do two really easy calculations. Basically, what we're going to do is take the first guy, which is 4.596 minus 2x, and set it equal to 0. We're then going to solve for x, which means 2x goes to this side, 4.596 divided by x. X in this case will equal 2.298 moles. We're going to do the same thing for our other reactant. We're going to set it equal to 0. So 3.763 minus x is equal to 0. You can see very quickly, hopefully, x is equal to 3.763 moles. Any questions on that two little calculations right there? By the way, if you get really good at it, you could just look at the guy on the left and go, I just need to divide it by 2, right? The guy over here is basically what it equals. What we're looking for is the smallest number of moles that we solve for x, and it would be this guy right here. This is the smallest. And what that means is, in this particular example, the aluminum then would be our limiting reagent. By default, this guy would be our excess reagent. And we're not going to use this calculation. So we're going to get rid of that number. And we are now pretty much at the point where we could answer every single question probably ever asked in a problem like this. Why is that x important? Well, if we look at that x and we look at our table, This is X right here is the same X that's here, same X that's here, same X that's here, and same X that's there, which means we very quickly and within one or two calculations can figure out everything that we need. So why don't we start with what was originally asked, which was aluminum oxide. So when we go back to our table, we see that the moles of aluminum oxide equals X. And what we see is down here from our calculation, X equals 2.298 moles of aluminum oxide. So just that quickly, we now know how many moles of aluminum oxide was produced. We could get the molar mass of aluminum oxide by taking 2 times 2698 grams per mole plus 3 times 16 grams per mole for our oxygen. Tells us that the molar mass of aluminum oxide is we'll call it 102, I guess. 102 grams per mole. So to answer our original question, we could take our 2.298 moles of aluminum oxide using the molar mass from the periodic table. We can convert those moles into grams, and that will tell us that we have produced, by punching maybe the right numbers there, 234 grams of aluminum oxide. That would be our theoretical yield here. First off, any questions on that first part of the calculation there? So why is this sort of method maybe a little bit beneficial? It's beneficial in the sense of, okay, let's say in this problem, I also want to know how much iron I would produce. I can very quickly figure that out by looking at my table and seeing that, where my pen went there, there it is. We see that iron at the end equals 2 times X, right? Which means I would take 2 times my X value I had originally, which was 2.298 moles. And now I could very quickly figure out that the amount of iron that would be produced in this reaction is 4.596 moles of iron using the molar mass of iron from the periodic table, which was 5585, right? I can, again, like I said, relatively easily figure out now that I would have produced 250, looks like 7 grams. 257 grams of iron would have also been produced in this particular case. So you can see it didn't take me very long to also figure out how much of this guy I produced. The other nice benefit of this is very often in these type of problems, they will ask you something like how much of your excess reagent is left over. Now, normally, if you do sort of a regular sort of limiting reagent type calculation, you might have to go all the way back, do a few other type of calculations. But in this case, we already know that our iron 3 oxide was our excess reagent. We also know that when we're done, the iron 3 oxide would equal this from our table. So that would tell us the leftover amount of our iron 3 oxide is 3.763 minus X. Again, using the same X value in all these, that would give us 3.763 minus 2.298. And again, these are moles. which would be 3.763 minus 2.298 gives us 1.465 moles of our iron 3 oxide left over. And if we want to know how many grams that was, we could use our molar mass that we had up here, same molar mass, and we can go 1.465 moles. Our molar mass being the same as above there, 159.7 grams per mole. And we find that we have about 234 grams of the iron 3 oxide left over. And that's, again, a very common thing that's asked in sort of limiting reagent problems is how much of that excess reagent you would have left over. What does all these numbers mean? So a couple of things. The theoretical yield of aluminum oxide would be 234 grams. This here, which is our other product, the theoretical yield of iron in this reaction would be 257 grams. And out of our excess reagent that we started with 601 grams, we would have 234 grams of it still left over. So we use there, whatever, 370-ish grams, 60 some odd grams of it to do this reaction. By the way, obviously you could put the X back into here, into our limiting reagent, but we should know that the limiting reagent should end up at 0 when it's all said and done. Yeah. So it should end up at 0 because it is a limiting reagent. Any questions on any of those steps? And again, if you get the hang of this sort of method of solving these things, like I said, it can really be a very good sort of time saver. And it can allow you to, like we just did here, it didn't take me a lot of effort to pretty much figure out everything you would ever want to know about this reaction, how much of the other product was produced, how much of the excess reagent was left over, by simply just going back and plugging our X value into everybody. Any questions on any of that there? So again, this is probably a new method for most of you, maybe not, I don't know, but most people probably don't learn this very much until they get to 200B. This is also, again, a very similar type of calculation, a little bit different application in 200B that the ICE table you do a lot of as well, but can be very convenient. So let's just take a moment and sort of talk about maybe another approach that sometimes people will do in these sort of limiting reagent problems. And I think it's here. So sometimes what people will do is do a simple sort of stoichiometry problem, and I'll explain what's going on in this calculation, and I'll put it up here so you can review it later if you'd like. But what they're basically doing here, which is another approach for limiting reagents, is they're basically doing a simple calculation between the two reactants. So basically what they're trying to do here is to say, if I want to use up 100% of all of my aluminum that I started with, which is the 124 grams, they want to know how many grams of the other reagent is needed. And that's basically what this calculation is telling you. Now, once you do that, you would compare, this is how many grams of the iron 3 oxide that I need. This is how many grams of the iron 3 oxide that I started with. And that would tell you the exact same thing that we learned in our table, that this guy is the excess reagent because you have plenty, right? You only need 367. You have 601 that is needed. And this guy would be our limiting reagent. So this is, again, another common approach to figuring out which one's the limiting reagent, is to take both reactants, do a basic stoichiometry calculation, figure out how much of one reagent you would need to use up the other reagent completely, and compare your starting amounts to that number and see if you have enough. If you have enough like we do here, that means, again, that that would be your excess reagent and the other would be your limiting. If you end up with not enough, then that guy would be your limiting reagent. Once you would determine that, you would then do a separate calculation from aluminum, which is our limiting reagent, to our product, and you'll come up with how much you would produce. So this is, again, another very common limiting reagent approach. Once we figured out aluminum was our limiting reagent, now we could do just a stoichiometry problem, and looky, that's 234 grams of aluminum oxide, just like we got before. And so that's, again, another very common way to figure out limiting reagents and to figure out how much you would produce. Um, the third most common way that people do it is to do two separate calculations like we see on the screen here. One like this, starting with aluminum, and then do one where you would go from grams of this guy all the way to grams of aluminum oxide. And you would basically do two separate calculations, and you would compare whichever one is the smallest would be your limiting reagent and your theoretical yield. So that's a very common way as well, which in this case you would see you would make more out of this guy. So those are the three sort of very common approaches. Maybe the disadvantage in this approach, or the approach we just saw here, is if you wanted to go back and then figure out how much iron, you got to go back and kind of do a whole separate calculation. You want to figure out how much of your excess is left over, you got to kind of go back and do another calculation. Again, the benefit of the ice table approach is you can kind of figure those things out very quickly without having to back up too far and kind of start again. So, if you are learn sort of this approach, which is a very common approach, you could absolutely continue to use it. I don't really have a preference on making you use an ice table or anything like that. But again, it might be a more convenient way to do these problems and a way to figure out things very quickly. But if you're comfortable doing it another way, you're perfectly fine to continue to do it that way. Any questions on that? So right there, it's basically three different ways you could kind of work out these problems. As I told you before, there's a multitude of ways you could kind of work these things. Okay, so let's talk about some other things. We kind of touched upon it a little bit here, which is theoretical yield, reaction yield. So yields are really, how much product you produce in a reaction. So yield is basically products there. So that's why when we talked about figuring out how much reactant we made, it really wasn't a yield. There's two types of yields. There's three really, but one's a theoretical yield. And the theoretical yield is really your maximum yield. And that is the one that is based off of the actual chemical equation or reaction and stoichiometry. So like the calculations we were just doing when we figured out 234 grams of aluminum oxide would be produced. That's our theoretical yield. As I mentioned before, what that really means is if everything went perfect 100% of the way perfectly great, nothing bad happened, no side reactions or anything like that, that is in theory how much product you should produce. We know life is not perfect, so we actually have the actual yield. And much like the name implies, that is actually when you did the experiment, how much you actually produced. Most of the time, your actual yield is less than your theoretical yield. And we can measure that by calculating something known as percent yield. We take our actual divided by our theoretical times it by 100%. When we do percent yield, we are looking for a high number. In the 90s is really good. Yes. 95% yield, pretty good. 98% yield, pretty good. 2% yield, not so good. Probably means you spilled things all over the place, dropped your thing, lost your thing, something bad really happened for you. So unlike percent error, stuff like that, percent yield, we're actually looking for a high number is actually pretty good. Can we have a percent yield over 100%? The answer is in reality, yes. Also, in reality, that usually means also an unhappy face because probably something went really bad for you in that case. And it can happen, but it's usually not a good thing. It's usually some type of error has occurred. Very commonly, sort of thing where that occurs is For example, if you did like a precipitation reaction, maybe you did a precipitation reaction and you got that precipitate, you filtered it through here, the liquid part went through, you had a filter paper that had the solid, you take the solid and the filter paper off, and you go to reweigh it. But you were in a rush because you had places to be, people to see, and you decided, I don't really need to make sure it's really dry. It's okay. It's semi dry, it's dry ish. And you weigh it, and maybe it's a little wet still. And when you weigh it, you're thinking you're getting the mass of your solid, but you're getting a lot of the water weight that's still on your filter paper. What that's going to do is make your actual yield higher because you're basically measuring water instead of the actual crystals you should be measuring. And that's going to give you a over 100%, which means probably not so good. So that's a very common sort of experimental place where people end up with over 100% yield. And it's really because they kind of messed up a little bit along the way there. Any questions on that one there? Okay. All right, so why don't you try one here? We have this equation here. We are starting with TiCl4 and magnesium. They're nice enough to give you the molar mass of each of those things, so that's good. We want to calculate a couple of things here. We want to calculate the theoretical yield of Ti and calculate the percent yield if we produce 5.42 times 10 to the 6 grams of Ti. So take a few minutes, see what you come up with, and then we'll go over it. You might just need Ti, which I think is 4788 as well. All right, take a few minutes and see what you come up with. Okay, so since we're getting towards the end here, let's take a look at it, see how you're doing. So, a couple of things. We obviously are given the grams of both of our reactants, so that automatically tells us this is some type of limiting reagent problem. Because we have grams, we definitely can get the moles of each of them. We're looking for the theoretical yield and the percent yield. So remember, the percent yield is our actual divided by our theoretical times 100%. This guy right here is our actual yield, so we actually have that. The theoretical is going to come from our calculation. So because it's a limiting reagent problem, we want to roll through our sort of steps to do that. That again is going to allow us to figure out the theoretical yield. First step is we have a balanced equation. Second step is let's convert these guys into moles. So starting with the TiCl4, they were nice enough to give us the molar mass there, which is 189.7 grams per mole. And that would get us for this guy 2.46. Make sure you use your exponent button on this guy. And we're going to do 189.7. And that is looking like, we'll call it 1.3 to the 5 in this case, maybe. 1.3 times 10 to the 5th moles of TiCl4. We're going to do the same calculation there for our other reagent. So that is going to be 1.13 times 10 to the 7 grams of magnesium. Also from the periodic tables where we get this number 2431 grams per mole. Going to get us 1.13 exponent 7 divided by 2431. Going to give us 465 to the 5th as well. Any questions on sort of that step again? Sort of the second step, like normal. Okay, so again, I'm going to go with the ice table approach here so you can again see it like one more time at least here. So to start it, I'm just going to rewrite the equation. Remember, making sure it's balanced, and I got the correct coefficients there. So we're going to start with our initial, which are the moles we just calculated. So for this guy, it was 1.3 times 10 to the fifth. And again, those are moles, just to remind you. Magnesium was the 4.65 times 10 to the fifth. And remember, like normal, we're going to start with 0 of our products. The change part, as we talked about, really important. We're going to have less reactants. So it's going to be minus x because the coefficient here is 1. This is going to be minus 2x. Again, if we don't take that 2 into account, we are going to have the wrong stoichiometry mole-to-mole relationship. Coming to our product side, it would be plus x and plus 2x. Any questions on the change part there? Now we're just going to carry everybody down. And again, so it doesn't look so messy, I'm going to leave the moles part off. So that's just going to be 1.3 times 10 to the 5 minus x, 4.65 times 10 to the fifth minus 2x, x, and 2x. So again, just really carrying down initial to the end there. We're going to do our kind of quick little calculation for both of them there to help us determine which one is the limiting reagent. So this one is pretty straightforward, is 1.3 times 10 to the fifth minus x is equal to 0. That means x is equal to 1.3 times 10 to the fifth moles. Setting our second guy equal to 0. Moving my 2x to the other side, which basically means I'm going to divide this number by 2. Gives us 4.65 to the fifth divided by 2. 2.33 to the fifth, looks like. 2.33 times 10 to the fifth moles. Any questions on that calculation? Now, we use this calculation to help us determine the limiting reagent, and we're looking for the smallest x value. And in this case, this is the smallest x value. That means we don't need this. Also means that we have now determined that our TiCl4 is our limiting reagent. By default, that would mean that the magnesium here is our excess reagent. Once you're able to determine the limiting reagent, you could determine which one is the excess reagent, and vice versa. If you can determine the excess, then you can determine the limiting. It's just one or the other. At this point, just like in the last one, although it doesn't ask for all that stuff, this x that we have here is every single x we have in this table. And as we talked about last time, that will very quickly allow us to pretty much calculate everything. So since we're getting to the end here, we'll keep it to just what it asks for, which was what is the theoretical value of Ti? And we can see from the table that at the end, the moles of Ti equals x, which means in our case, that means we have 1.3 times 10 to the fifth moles of Ti. We then could use the molar mass from the periodic table of Ti, which was 4788, to convert those from moles into grams. And if we do that, 1.3 to the 5 times 47.88 gives us 6.22 times 10 to the 6th, I believe, grams of Ti. This would be our theoretical yield. Any questions up to that point? To calculate our percent yield, we would take the actual divided by the theoretical times 100%. So remember, our actual was given to us in the problem. Is that 5.42 to the 6 divided by our theoretical that we just calculated, 6.22 times 10 to the 6 times 100%. And that would get us looks like 87.1%. not terrible yield, so it's at least in the high 80s, I suppose. Question on any of those steps? And again, you could, if you wanted to, or were asked, how much magnesium chloride, you could put the X value into there and figure out the moles, use the molar mass and figure out, how many grams you would produce pretty quickly. If you want to know how much of the excess reagent was left over, you could put the X value into this. And that will give you how many moles of your excess reagents left over. And using the molar mass of magnesium, you could figure out how many grams you would have. So again, you can very, very quickly, figure out all kinds of things that are typically asked in these type of problems. Any questions on sort of stoichiometry, limiting reagents? Okay. All right, so we'll stop there